Again, thanks for having me out here. We've got a course here, Process Certification Defect Recognition, that's really a compilation of things I've been doing over the past 10, 15 years, going back to my days when I used to work here at Lockheed, actually right here in this building up on the 3rd floor. So it's kind of nice driving back and coming into the plant today. But you know, I couldn't agree with Ray more about the importance of finding these problems before they get into a qual failure, before the hybrids are built up onto boards and into black boxes. That's, you know, when you think about the cost and the effort to diagnose those kind of failures and to be sure about what caused the failure and to what extent it affects other spacecraft or other boxes and so forth. It's just a tremendous resource strain, which really, in many cases, can be avoided with some good engineering and some good judgments up front. It's always easier to, you know, find a defect the earlier you're at in the production flow. You know, for example, if you've got a MMIC and it's a bad MMIC, you don't die attach it. If you've got a die that's already put down in a hybrid, you know it's bad, you don't wire bond it. You know, just the earlier you can identify these problems and defects and materials and process issues, the better off you're going to be as a group and as a company. So let me give you a little bit of my background just so you know where I'm coming from. Actually grew up in the general Philly area. I'm from Bethlehem, went to school at Lehigh in materials and process. Got into the Air Force. I worked at a place called RADC, Rome Air Development Center. They were responsible for the technical content in Mill Standard 883, which is one of the default specs that people turn to in terms of building hybrids. So there I was fortunate enough to get in and out of a lot of different hybrid facilities and do failure analysis on components, primarily hybrids. In '89, I came out here to Denver, worked for Jim Beal and Mike Rossman, and there used to be a hybrid lab, as I mentioned, up on the 3rd floor here. So I had a chance to do wire bonding processes, component attach, hermetic seal. These are all the fundamental processes for manufacturing a hybrid, an RF MMIC module. I'll get into what these terms mean. Multi-chip modules. It's basically working with bare die and wire. In '94, I went back to Valley Forge area and was again involved as a material and process guy. Worked with the A2100 program, so I also had some experience on the commercial side. In the '96 time frame, I left and worked at a local college up in Bethlehem, and for about 10 years was able to develop some of the curriculum that I'm using now. And since 2002, I've been on my own, and basically I spend half my time as a consultant and the other half teaching some of these core courses. A lot of them geared towards quality, but I get a lot of quality engineers take the course, manufacturing engineers, designers, and I teach at other Lockheed facilities and Jet Propulsion Lab, and I'm very kind of in tune with the space community. My background is really from a materials process standpoint. And as we go through this, you're going to see I have a lot of pictures. With each picture comes a story. And I'm going to try and take, this is actually a 4-day course, which we condensed down into 2.5 days. And then with what Ray and Roger told me, I'm going to try to, keep it on the mark for the engineers that are sitting in here. But I want it to be interactive, so So as I get to a slide, or you're not understanding what I had to say, or whatever, you've got a similar problem, then please share it with the group, and I'll do what I can to guide you. Or at the end of the day, it comes down to making good decisions about the hardware, because there's a lot of people, of course, that rely on these satellites. I'm actually a retired colonel in the Air Force, and I know a lot of people that the defense of the nation rests on some of these systems. So the decisions you make, especially early in a program, can be very critical and either lead to success or come back and haunt you in the program. So let's go to what we're here today for. Basically, this is our focus to get an understanding of the basic materials and processing steps for building hybrids. I call them hybrids, microcircuits, RF mimic modules. I'll get into what that all means in a little. Along with your books, the student handout book, which is basically a copy of all my slides, everyone should have received a workmanship standards, which is a document we put together about 10 years ago with manufacturing engineers, quality engineers, some designers. At the time was a Lockheed Sanders facility. It's since now become a BAE Systems facility, but the pictures in that disc is pretty much augments the course. We're probably not going to go through all those, but after listening to what I have to say here, some of those pictures are in the course notes, but that'll be a resource for you in the future. And the password, before I forget it, is TJ Green LLC. It's a PDF, and it's a password to get into the PDF. But again, getting back to this course, we're not just going to be looking at defects, although I am going to show you a lot of defects. We're going to be talking about the cause and effect. What was the process and the material issue that caused that defect? And then taking it a step further, what could have been done at the hybrid facility or within the program to preempt that defect from making its way into the hardware. So, that's part of it, is to, get comfortable with hybrids, see what they look like, understand the defects, be able to explain to people why it's a defect, and so forth. Okay, this is the CD, and we quit doing a hard copy book a few years ago when I realized how many trees we were wasting. But there's quite a few pictures in there. It's over 200 photos. There's an appendix. If you're not familiar with hybrids, that might be not an appendix, a glossary. I think I actually had here's the table of contents from the book. The first section talks about kind of the references. A lot of the hybrids are basically fall under the realm of MIL Perf 38534. That's your kind of your playbook or your overriding document. If you have a hybrid that's on what they call the QML, the Qualified Manufacturers List, then that hybrid manufacturer is living to the letter of the law to 38534. When I was back in Newtown and even out in here on some of the programs when Lockheed was building hybrids, we used to build to the intent of that document. So a lot of times some of the requirements in there, for example, 100% non-destruct bomb pull, sometimes they are tailored for cost issues and whatnot. But I'll be talking about that some more here in a minute. Getting back to the workmanship book, it's broken into 3 sections. Whoops. First is defects and issues with the individual chips that are brought in that make up the hybrid. Then we have what's known as pre-cap visual inspection. The fourth section is on external visual inspection. That's a look at the welds and the glass to metal feed-throughs, which, trust me, over the years, that's been a very contentious point within the hybrid community, looking at some of those glass to metal feed-throughs and trying to determine whether or not they're good or not. Then there's a few appendices. One's a typical manufacturing flow. The flow down requirements for visual inspection, and that goes from incoming to pre-cap to external. Get some checklists in there. Rework provisions. Within a hybrid, there's oftentimes rework. The important thing is that those rework procedures are documented and have been qualified. And then there's another couple of charts on a visual color chart for looking at gallium arsenide devices and silicon chips as well. And then, as I mentioned, a glossary if you're new to hybrids. And as we get into this, if I'm using terms you don't understand, please stop me. There's no such thing as a dumb question. There's a lot of information here, and it may seem a little overwhelming at times, but if you stay with it, you'll get the gist of it. So, as far as the course material, my own personal experiences, the workmanship standards I was just talking about. There's a couple of workshop conferences out there that are very helpful in terms of hybrid manufacturing. One is an IEEE ECTC. It's a conference, and there's the actual subgroup is components, CPMT, components, packaging, manufacturing technology. It's something along those lines, but it's a lot of good papers on wire bonding and substrate manufacturing and so forth. And the other group, which I've been heavily involved with over the years, is called IMAPS. It's International Microelectronics and Packaging Society. It used to be called ISHM, International Society of Hybrid Manufacturers. And actually, in our '97 conference in Philadelphia, we unveiled the new logo. And if you search back through those proceedings, just about any problem you're going to come across in hybrids, I would bet there's a paper or a reference out there that can help you try to keep from making the same mistake over again. I mean, hybrids have been around since the late '70s. In some respects, they haven't changed much. And a lot of the materials and the processes have gotten better. They're cleaner, they're more robust. But it's still, some of the same issues come back to haunt you. So as a, additional resources besides what I'm going to share with you today, those are two good societies. At the end of the notes are a few textbooks which you probably ought to order. Cheap enough through Amazon.com or whatever. Buy the used versions if you want. One's on wire bonding by George Harmon. There's another one on hermeticity by Hal Greenhouse. And there's a couple of good general books on hybrids. Jerry Sargent has a book. You can look at those at the end of the notes, and those are good references to have, especially if you're new to the game and you're just looking for what are the big issues, what are some of the things I need to do. And then finally, I'm going to be talking about a couple of mill specs. Two in particular is one I already told you, which is mill perf 38534. That's the general specification for hybrids. That's what everybody lives to by and large. And then out of 38534 is the 883 test methods. And That's what 883 is. Mill Standard 883 is nothing more than a collection of test methods. Somebody says I'm building 883, I don't really know what that means. If you're building a hybrid to 38534 and you're running the tests that are specified in 883 to the conditions that are specified for screening, qualification, element evaluation, now I know what you're talking about. So keep that in mind. All right, today I'm going to start in a little bit of an overview. I actually have some product I'm going to pass around, kind of typical hybrids and so forth. Talk a little bit about the processing of hybrids. And then I have two areas we're going to get into in a little greater detail, just give you an overview of semiconductor fabrication, conventional silicon type technology, and then the gallium arsenide fab. Gallium arsenide is a 3.5 semiconductor which operates at much higher frequencies, and the two devices look entirely different, and they each have their own peculiarities in terms of handling and typical kinds of defects and so forth. We'll also touch on gallium nitride, which is another device technology that's being used more and more. Foreign materials, a big part of building hybrids, trying to keep FM out of the product, and there's been more than one system brought down because of a loose wire or a loose particle inside the hybrid. So as you're out working with suppliers, you're going to make sure they have in place the proper controls for eliminating, identifying foreign material. And then this afternoon, we're going to get into substrate technology, thick and thin film. Thick film technology has been around for quite a long time. It actually originated in the Delaware Valley area back in Pennsylvania. And there's still some prominent thick film suppliers back there. This is, using a screen and resistor inks, conductor inks, printing them onto a ceramic and then firing it. For the higher frequency stuff, most of your RF mimic type modules, that's primarily thin film, which to the naked eye, it's kind of hard to tell the difference, but as you get down and look at it a little closer, there are some significant differences in performance and again in materials and processing of both those substrates. So, and then we'll also touch on laser processing, which is trimming the resistors to precise values to meet the design. So that's what today is going to be about, looking at the active components, they call it, the ICs and mimic devices, and the substrates that they go on, which then are packaged into the hybrid using epoxies and film. The substrates generally go down with film. The individual die go down with conductive epoxy, or in the case of a high-powered mimic, they'll use solders, but not the type of solders used at the circuit board level. More often than not, it's a gold tin or some sort of fluxless soldering process. That's one of the things that differentiates hybrids from conventional SMT circuit board manufacturing is, for the most part, within the hybrid, as best you can, you avoid the use of fluxes because of the ionic contamination. Ionic contamination with a little bit of moisture and a bias is what leads to failures in the field. It's what leads to qual failures. So people that are doing hybrids that involve solder processes, are running a fine line and really have to set up their process flow so that they were able to clean up the substrate or whatever needed to be soldered, and then go to typical hybrid bonding processes, which is, for better or for worse, using glue to stick them down, conductive, non-conductive epoxies, film epoxies. And we'll look at the test to determine the integrity of the bond and some of the issues you run into if it's not properly designed, and things that can result from that, cracking being one, and other problems. And a big part of hybrid assembly is the wire bonding. Wire bonding, it's all different flavors of it: ball bonding, wedge bonding, deep access bonding, ribbon bonding. So we're going to talk about wire bonding and the reliability of wire bonds, what to do to qualify and to make sure that the bonds that are made are the best they can be made. This is a real challenging part of hybrid manufacturing is the wire bonding. It's not like there's a single die on a lead frame. In Southeast Asia, they knock out a gazillion bonds a day. And it's a very repetitive process, a very high reliability, high yielding process. In hybrids, the issues are you have chips, multiple chips. You have pins that you bond to. You have substrates that you bond to. The surfaces aren't flat. They're generally dirtier. When you go to automate that, it's honestly becomes a nightmare in some cases. There's still a lot of manual wire bonding that's done. Again, from a design standpoint up front, you get a chance to review, some of the layouts. Things you want to avoid are like deep access wire bonding with 7/10 wire. Sometimes I get out in the field and I say to myself, why are you using a deep access tool? We'll talk more about that later. But there's some things up front with looping configurations, placement of the pads relative to the chip, design layout issues right up front that can, minimize problems. When you put a company in a position to, try to build something that really can't be built reliably, you're behind the 8 ball and you suffer with yields and potential problems that get into the hybrid and into the unit. So tomorrow is all about die attach and wire bond, and day 3 really deals with hermeticity. It's a topic that's near and dear to my heart. I'm actually an expert witness in a medical case because of a hermetic failure on an implant. It's something I've been involved with going back to my time here. Devices that fail residual gas analysis, which is looking at the moisture content inside a hybrid, problems with the sealing, problems with the testing. This is a big area of confusion when you flow down requirements. Are you speccing out an air leak rate or are you speccing out a measured helium leak rate? What were the preconditions? What is the true cutoff? What do you do when you fail a hermeticity test? Some of these units are, upwards of $5,000-$10,000 with a, $2,000 ASIC in the middle of it. So you lose, you fail the hermeticity test. What are your first steps there? What is RGA all about? What's that spec about? The 5,000 ppm. I want to save plenty of time on Thursday morning to really delve into that as best I can, and if nothing else, just really sensitize you to those issues, because that's one of the reasons lots get held up. It's one of the reasons you got to go in and tear down devices out of the spacecraft and so forth. So, and then we do have a test. It's really a review platform, if you will, to kind of go back over everything we talked about. So, take notes in your books or whatever, and feel free to ask questions. Any questions up till now before we start delving into this? Is everybody still with me? Like I said, I'm not used to sitting, and I'm looking out at a sea of, computer screens and heads bobbing in and out. Of course, I can't see anybody in Philly.